Hey, how's it going everyone? Welcome to this video on the definite integral. In this video we're going to have a look at what the definite integral is, calculating and evaluating the definite integral, looking at integration and area, and defining integrals in kinematics. So the indefinite integral is what we've been looking at in the last couple of chapters, and it's been used as a symbol for antiderivatives. The definite integral is what we're going to have a look at now and how to evaluate it. We're only going to explore briefly on its meaning and applications. So the definite integral, very much the same as the indefinite integral, except now we've got what looks like an A, or the same thing, except we've got A and B on the actual integral sign. So these A and B values are what's called terminals. And we've got an upper terminal and a lower terminal. Basically, the upper terminal is the one that's on top, which is B, and the lower terminal is on the bottom. Essentially, what we're looking at is, as I said earlier in an earlier chapter, we're looking at the area between a curve and usually the x-axis, but sometimes we look at two different curves and the area between them. So we might be looking at the area of the line y equals x plus 3, for example, and we want to work out the area that that curve makes between x equals 1 and x equals 3. So we're looking at this area in here. So this 1 would be my lower value as A, and this is my upper value or upper terminal B. So all we're looking at is we're finding the antiderivative between x equals 1 and x equals 3 for the line x plus 3 dx. And what we're going to have a look at is how we actually evaluate this. And we get this calculation. It's basically, if you remember, if we're starting with f of x, and we find the antiderivative of it, it's going to be this capital F of x. And that's what it is here. So that capital F of x is just the antiderivative of the standard f of x. And we put that value of b into it, and we take away the same thing, except now we've got a. Sometimes it's easier to do it in steps, and instead of doing it all as one big calculation, because it is going to be quite big, as you'll see as an example shortly. Sometimes worth in square brackets finding out what my antiderivative is first, so I can then use the values for a and b. So just breaking it up into steps, and we use this square brackets to indicate our antiderivative. So then we can use f of b take f of a. So that's important to know because that's what we'll be looking at in this next example. So we've got the antiderivative of 2x between 1 and 3. And as I said before, first thing, just work out what the actual antiderivative of 2x is. So we'd get 2x squared over 2. And if we simplify that, it's just going to be x squared between 1 and 3. And the next step is to work out what x squared for 3 is. Take away 1 squared. So here's my f of b take f of a. And if I evaluate that, I get 9 take 1, which is 8. Just notice over here where I found the antiderivative of 2x, I didn't have that plus c. And it's important to note that you could add that plus c, but it basically doesn't do anything, because when you work out this calculation here, if I had 3 squared plus c and then take away that plus c, they both cancel out by this negative sign. So we don't tend to write the plus c when we're finding the definite integrals. It just wastes time and calculations. So looking at another example here, we've got the antiderivative of 3x squared plus 1 between minus 1 and 2. So again, first step, just work out what the antiderivative is. So adding 1 to the power, dividing by the new power will give me x cubed, and then plus x between minus 1 and 2. And then I just put in my value for 2 for both of those. So that's f of b, take, oops, f of a, which is going to be minus 1 cubed plus minus 1. And this is where it does get complicated sometimes when you have lots of different negatives, so it's worth just doing it in steps. So I get 8 plus 2, take, and this will be minus 1 plus minus 1, which is minus 2. So as you can see, I'll get a 8 plus 2, 2 negatives make positive, so my answer will be 12. As I briefly mentioned before, we're finding essentially the area between two curves, and sometimes I haven't done an example, but sometimes we can get a negative value. So in this case here, we got a positive 12, but sometimes we get a negative value. And sometimes we might even get 0. And obviously area, when we're talking about area, we can only have a positive area. So when we get a negative value or 0, it doesn't make sense, or it doesn't seem to make sense. And that's where signed area comes into effect. So the straightforward, or the answer that we had a look at, is the first one where f of x is greater than 0. So it's talking about when my curve is above the x-axis. So when it's above the x-axis, I'm going to get a positive area, essentially, is what it's talking about, between A and B. So the area in there is going to be positive. Whereas an example where the curve is below the x-axis, I'm going to get an area between A and B for those, and it's going to be a negative area. So before I had positive 12, well, if I found out that it was actually the area was negative 12, it just gives a value for a signed area. So by ignoring the negative sign, the value of the integral will still measure the actual area. It's just that we're talking about it's below the x-axis. The other option is where it's partly positive and partly negative. So if I have a curve, oops, so if I have a curve where it's both on above the positive and it's also below the positive, or below the x-axis, I'm going to have some positive over here, and I'm going to have some negative values over here. So when we're actually evaluating the definite integral, it's the sum of the signed areas. So it'll be, if I found it between x equals, let's say that was 0 and x equals 10, for example, this might be, let's say, positive 6, whereas this might be minus 2. We work out the integral, and it would be the sum of those two values. So I would get a area of 4, and it's not really useful for us because I want to find out what the actual area is between those, where I should get a 8 for those, because it's the area of this plus the area of this will give me 8, whereas working it out as one big thing will give me 4, which I don't want. So obviously this adds complexity using the signed area to measure the definite integral. Um, and essentially um, that's as far as we're going to get in this part of the course. Next year, when you look at units 3 and 4, you'll be looking at how do I work out the actual area between positive and negative partly areas. You might already be able to see a possible solution to working out those, but I'm just going to leave that for now. Moving on to worked example 9, we've got an area bounded between the line y equals 2x, the x-axis, and x equals 0 and x equals 4, as illustrated as shown. And I want to work out what this area is in here. A couple of different ways I can work it out. First thing is by geometry. As you can see, I've got a triangle, and I can work that out by a equals half base times height. At the moment, I don't know my height, but I can work that out because I know what the line y equals 2x. And my height is going to be this point here when x equals 4. So when x equals 4, I'm going to get 8. So my base is going to be 4 times, and that's going to be 8. So I should have 16. So that's just by working out by geometry or just by the formula of a triangle. Now talking about the definite integrals. So if I wanted the definite integral, okay, I still have that long s, and my lower terminal is 0, so it's between 0 and 4, which is my upper terminal. My function is 2x, and don't forget your dx at the end. So that would be the definite integral, and now I can work that out for part C. Again, just work out what the antiderivative of 2x is, which is x squared, and then put in my values. So I'll have 4 squared take 0 squared, which gives me 16. Same answer, two different ways of doing it, gives me the same result. Just finishing up with the definite integral in kinematics. So if we have a particle traveling at a constant velocity of 2 meters per second, it'll travel a distance of 10 meters in 5 seconds. So for this motion, the velocity time graph is a horizontal line, as I've shown here. So we're moving 2 meters per second, and we work out the distance. By drawing a diagram, again, I can work out by geometry the area underneath, which is, well, height of 2, length of 5, which is 10. That's where that 10 meters comes from. And so what we can say is the area under the velocity time graph will give us the measure of the distance traveled by the particle. And again, if you remember, our distance x and velocity v, we can go from one to the other, x to v, by finding the derivative. And when I find the antiderivative, before we were looking at the indefinite integral, now we're looking at the definite integral, which will give us the area under, or in other words, that will give us the distance travelled. So that's just what we're looking at in kinematics. So work example 10, we've got a velocity of a particle moving in a straight line given by 3t squared plus 1. Give the particle's velocity and acceleration when t equals 1. So first thing is looking at the velocity at t equals 1. So v is going to be 3 times 1 squared plus 1. So that'll be 4. Acceleration is going to be the derivative of the velocity. And if I work that out, it's going to be 6t. And at t equals 1, I'm going to have a is equal to 6. Part B says sketch the velocity time graph and shade the area which represents the distance over the time interval 1 to 3. Okay, so I've got my set of axes. I've got V, velocity time, so V and T. It looks like I've got a quadratic, T squared plus 1. It's going to look something like this. At V equals 1. And I'm after the area between T equals 1 and T equals 3. So it'll be this area in here. And we need to use a definite integral to calculate the distance. So the integral is going to be our velocity between 1 and 3 dt. And if I work that out, adding 1 to the power and dividing will give me t cubed plus t between 1 and 3. So now I have 3 cubed plus 3 for the first terminal. Take 1 cubed plus 1 for the second. So I'll get 30. Take 2, so about 28. So therefore I can say the distance travelled by the particle over the time interval 1 to 3 is 28 meters, which is the area under there. So that's it for the definite integral at this stage. As I said, when we go into units 3 and 4, we'll be expanding on the fundamentals as we've had a look at so far. That's it. Thanks for watching.